In a previous video, we looked at the 68, 95, 99.7% rule. It's not exact, it's a rule of thumb, but it'll give you a rough idea about what the area under a normal distribution, under a normal curve would be for these intervals. Now, this rule only works for these 7 values of x, okay, whatever your variable is. If you want to calculate the proportion for some value of x that is not one of these 7, this rule is not going to help you. But fortunately, there are other ways to solve problems like that, and most of them rely on the so-called standard normal distribution, or Z distribution, which is normally distributed and has a mean of 0 and a standard deviation of 1. Now I've drawn a normal curve and marked the axis with a Z instead of an X. The mean here is at 0, and then I have 1, 2, 3 standard deviations on either side of the mean. The areas in each of these bands are the same as the areas that we got with the 68, 95, 99.7% rule. But the nice thing about this Z distribution is that it's been studied extensively for about 200 years, and we know a lot more about it than just those very rough estimates that we got with that rule. Any normal distribution, if you have any variable x that's normally distributed with a mean of mu and a standard deviation of sigma, you can transform that into a Z. Okay, you can transform the variable into a Z, transform the distribution into a Z distribution using this linear transformation. You just subtract the mean mu from all of your x values and divide the result by sigma. Now this is a linear transformation. Subtracting the mean mu moves the distribution so that its center is at 0, and then dividing the results by sigma changes the standard deviation or spread of the distribution so that the new standard deviation is 1. Now, the nice thing about this is that any linear transformation that you do to a normally distributed variable is going to preserve the shape of the distribution. So Z will also be normally distributed. Now, proportions under this curve have been studied extensively, and they're very easy to find nowadays with the technology that we have and with the background knowledge we have. If you want to find a proportion in a Z distribution, you can use a table or you can use a calculator. If you have a TI-84, this is the basic syntax. You type second and then vars and then 2, and that pulls up this expression normal CDF, and you type in a left bound and a right bound for the area under the curve that you're interested in, and then when you press enter you get your result. So if you want to calculate the proportion of z-scores that are less than 0.45, this is a basic sketch of what we're looking at. Here is our z. On the axis we've got the mean 0 marked, and we've got the boundary value 0.45, which is to the right of 0. We're looking for this area to the left. Okay? Now, if you do this on the calculator, you go second vars and you pull up normal CDF, and then you have to put in a left bound. Well, the left bound technically is negative infinity for this distribution, and you can't use that because your calculator can't handle a number like that. But you could use a number like negative 999, or any fairly large negative number would work, and then put in your right bound 0.45. And when you press enter, it will give you that proportion right there that's illustrated, and that is 0.6736. Okay? If you want to find the area to the right of some value, say you want to find the proportion of z-scores that are greater than 0.31, well, that can be done. I've got my picture here with my z distribution and the mean marked 0 and then the boundary value of 0.31 marked. I want this shaded area to the right. The calculator can do this very easily. You just go second vars, select number 2, and then you put in 0.31 as your left bound, and then put in 999 or some other large positive number as your right bound, and we get 0.3783 approximately. And that's all well and good. Now, if you want to find these things with the table, it's not too hard, but it's not quite as easy as with the calculator. And here's why. If you want to find the proportion of z-scores that are, say, to the left of 0.45, what you're going to have to do is find that z-score on the margins of the table. And this has the first decimal place of any z-score in this column right here. And you're going to go down to 0.4 to that row. And then you have to go across the top to find the second decimal place in 0.45, which is here, 0.05. And where that row and that column intersect, you'll see the proportion you're looking for, which is 0.6736. So that's not too hard to find, but just remember that this gives you the first decimal place of your z-score, and your second decimal place is up here. It won't give you any better precision than that. 2 decimal places for your z, okay? And on your calculator, you got about 10 decimal places for your proportion. This table will only give you 4. So it's not as precise as the calculator might be, but in most cases, this is good enough. If you want to find the area to the right of 0.31, well, you can go to your 0.3 row and go over to your 0.01 column, and you see 0.6217. And you say to yourself, hey, wait a minute, 0.31 is to the right of the mean. That means this area should be less than 0.5. And it's not. Well, this is the area to the left of 0.31. If you want the area to the right of 0.31, you're going to have to subtract this from 1. And you get about 0.3783 thereabouts. And that's not too hard to do. But remember, these are all left tail areas. And if you want an area and a right tail, you're going to have to subtract these from 1. Now, on the calculator, you can also do calculations like this. Suppose you want to find the proportion of z-scores that are between 2 values on your number line. And as I have it here, I have negative 0.52 and positive 0.89. If I want to find that area with the calculator, it's very easy. All I have to do is go to normal CDF, and then I put in negative 0.52, and then I put a comma, and then positive 0.89, close my parentheses, press enter, and I get 0.5117. Very simple. Okay? If I want to do this on the table, I'm going to have to find the area to the left of negative 0.52, and then find the area to the left of 0.89, and then do a subtraction. And that can be done, but it's just not as convenient as doing the calculator. The calculator can do this in a snap. Looking up these two z-scores and the corresponding proportions in the table takes a while, and then you're going to have to do the subtraction correctly, and that's a potential pitfall. So I recommend that you do the calculator anytime you have to do any of these calculations, really, but particularly when you have to do a right tail calculation like that, or a finite interval calculation like that, either one. Now, what the calculator gives you with normal CDF is the percentile. If you do normal CDF negative 999 comma z, that'll give you the percentile that corresponds to a given z, which you type in there. If you want to go backwards, you want to find the z that corresponds to a given percentile, you can do this. Go second vars 3 and use a thing called inverse norm that's on there. And the syntax for that is you have inverse norm, and then you type in the percentile that you're looking for as a decimal, and then the output of the calculator in this case would be the z-score that corresponds to that percentile. So, for example, suppose you want to find the percentile or the z-score that corresponds to the 25th percentile. So you would have to input 0.25 as your percentile. So you go second vars and number 3, and then you type in 0.25. Well, this is the first quartile of the distribution, basically, and that's negative 0.6745 approximately. Okay? Now, the distribution is symmetric, so the 75th percentile should just be the opposite of the 25th percentile, and it is, and we can verify that if we go to second vars 3 and type in 0.75, we'll get positive 0.6745. Okay? Now you can find other important percentiles under a normal distribution. The 10th percentile you get by going second vars 3, and then you type in 0.1, and you get negative 1.2816 approximately. The 20th percentile, same thing. You can recall that command and just replace the 10 with the 20, and you get negative 0.8416. And then if you want the 30th percentile, do the same thing. Recall that command, overwrite the 2 with a 3. Press enter, you get negative 0.5244. And then if you want the 40th percentile, well, second VAERS 3.40, and then negative 0.2533 is the z-score that corresponds to that percentile. Okay, so the calculator is very useful for going both ways. You can use the calculator to find a percentile that corresponds to a given z. You can also use it the other way to find a z-score that corresponds to a given percentile. If you want to do these calculations with the table, it's possible to do that, but it's a lot trickier. What you have to do is find the percentile in the body of the table. So say we're looking for the 25th percentile. You have to look around in here and find a number that's close to 0.25. And here's one, 0.2514, and here's one, 0.2483. So this one's slightly closer to 0.25. And if you go across that row, you'll see that the first decimal place is, or the first 2 digits are negative 0.6. And then if you go across and go up to the top, you see 0.07 is at the top of that that column, and so your z-score is negative 0.67, which is what we got with the calculator, but the calculator gave us 2 extra, or actually a lot more extra places, decimal places of accuracy, and so this is not as precise as the calculator is going to be, and I recommend that you use the calculator for all these kinds of calculations.